Uh, in this video, I will explain you how you can calculate the weak point and the maximum safe pull, minimum pull out, and maximum pull out for your wireline operations. It is a very important parameter for any wireline operation, and that has to be calculated before each violent job. So before coming on to the weak point calculation, I will just give you a brief overview of some of the basic concepts related to the tension and the weight, which you might have covered in your engineering degree, but just for a revision. And one assumption that we take uh, in our theory classes, but we generally, but we consider it in the real life. So, like if this is the block and that weight is W1, any number, okay, and her cable is being connected to that block, and that is a sheave through which our cable is being passing. If if we go back to our, and here we got a tensioning measuring device at that point. At that point we are measuring tension, okay. So if we go back to our static dynamic class, we will remember that we ignore the weight of the cable. We don't consider the weight of the cable. So if the weight of the block is like 10 Newton, the tension that will be appearing on this tension measuring device will be equal to the 10 Newton as per our theory class. But in real life, we also have a weight of the cable, and specifically for the wireline cables, they are very rigid and very strong cables. So they have a very high weight per unit feet or per unit meter. So if the cable weight is 10 Newton per feet, and that length is 20 feet, okay. So the 10 Newton per feet, and we got a 2 feet, so that weight is 20 Newton. So 20 Newton plus 30 Newton, so the combined tension that will be appearing on this tension device will be equal to the 30 newtons, not the 20 Newton. And as we go on increasing, as we go down, as we do in our oil well during wireline operations, the length of the cable kept on increasing. So weight per unit length would kept on increasing. So if we add 10 feet, then the weight of the cable would be 100 feet, but also the weight of the block will be 10 Newton. So the combined tension that will be appearing, if we go for 10 feet, we can have 10 feet in the depth well, that will be 100 newtons, and combine the weight of the tool string, that will be 110 newtons. But this is just an arbitrary number that I have explained you. If you want to check out like your cable, what is the weight of your cable in what is your weight of the cable per unit length, you can refer to your cable specification through Camisa website. But other factor that you might have remembered from your FSC class is the buoyancy factor, buoyancy force. Sorry for the spelling. uh, Buoyancy force. So we know that if something weight like 10 Newton in air, if you put it into water, the weight will decrease because water will exert an upward force on it. So the weight of the object decreases as we move it into water. So these are the two concepts that we are gonna use. And we know that for oil well, the well has a fluid inside it. If it's in production well, so that will be equal to the weight of the crude oil. So if the weight in the air is 10 Newton, so definitely the weight in the crude oil would be less. So moving on to the slide part. So the two parameters that we need to find out, what we need to find out at what depth we are standing, and what is the weight of our cable in that fluid. Okay, but we don't need the weight of, we only need the weight of the cable in that fluid. That can be a crude oil, or if it's an open hole, then it can be a mud. But we don't need the tool weight of the tool that is connected to the wire line. The reason is because when the tool gets stuck, uh, it will be held up by that stucking point, and the only thing that will be acting on that, or that will be only connected, is the cable to the or drum, not the tool string is being connected, because tool is being stuck at the point. So we don't need that. We don't use that in calculations. Moving to the slide part, question is why we need a weak point. So if the tool gets stuck in the well and we want to move or free, want to move our tools, if we want to uh, move out, then what we have to do is we have to uh, free the cable from the tool. Then we will use the fishing operations to get our tool out. Okay. If we want to factors that affect the cable, the tool, we want to note that the fluid, what is the fluid in the borehole, and what is the mud weight, what is the weight of that fluid in that well. So that will affect or weight of the cable in the mud. Because as we know from the Beyonce, we know from the physics principle, if the weight decreases, weight of the cable decreases as we move downwards. As we move the fluid, the weight decreases because the fluid exerts upward force on that. So what we want to do, we want to find out what is the uh, weight of the mud, friction, pressure, and obstruction if there is an obstruction in the well bore. So this is the same concept that I have explained to you. We got a tensioning measuring device at this position at an wheel, and the tension varies as a function of the length. So if we are at 5,000 feet, the tension at this point will be 485 pounds. And if we are at the bottom of the well, then the tension at this will be 10,000, 970 pounds. So we can say that the tension varies as a function of depth. And maximum tension for the cable for this whole system will be at the bottom of the well bore. So we measure tension here, and we don't measure the tension at this point, at this point, at this point. We only know the maximum value of the tension that is being at the top of the wheel. And when this value will be maximum, when the cable is at its maximum depth. This is from the basic design to a construct that we can survey out a wireline link to the tool and maximum depth we will reach. Why? If we can, the reason is that if we can break or weak point at maximum depth, we can break it at any depth above. So if a tool construct, then we can simply uh, uh, then we can simply break or wireline from that point. I will share the slide with you. Don't worry. So when the tool is stuck, the tool weight is not supported by whatever is holding the tool. Therefore, tool weight does not act. As explained earlier, when the tool becomes stuck, the tool is being supported by whatever is holding it. The only thing that is being acting on the weld and cable is the weak point, is the weight of the cable. So we need to apply the tension on it. We know that we can never exceed 50% breaking strength of the cable. So if the breaking strength is 1,000 pounds, we should never apply the tension greater than 500 pounds on the cable. So we got two tensions. One is the tension when we apply the tension on the cable. We got the two tension. One is the tension due to the cable weight in mud. So if the cable weight is like 10 pound per feet, and we are at 10 feet, so the cable the tension that will be appearing on the or on the tension device will be 100 pounds. But and then we apply the tension on the weak point. So that will be the combination of the two tension, and that should never exceed 50% of the breaking strength of the cable, because when the tool becomes stuck, there is no tension that is being applied on. There is no tension that will appear on the weak point, because unless or until we start pulling or winch. So weak point should be, if we arrange the equation, we get an half weak point should be less than half breaking strength of the cable minus cable weight divided by maximum depth. So the unknown is, we know from the clear specification what is the cable breaking strength, and we can calculate our cable weight in mud and maximum depth. This is the formula that we used for calculating the cable weight in mud, which you just simply had to put the, you just need to know the density of the fluid and well bore fluid, and you can calculate the weight of the cable in that mud. Now, the formula for calculating the number of armors, there are two armors, one is the outer armor and the inner armors. We only use the outer armor for calculation. However, there should be minimum two or three inner armors, because that will prevent the rotating effect of the cable. So if inner armor is exerting clockwise torque, the outer armor will exert counterclockwise torque. So is the formula that we will use for calculating the number of outer armors. So just multiply our outer armor strength with 0.5. So this is an example of it. So this is, we know parameters are given, which is weight in air, weight in cable, outer breaking strength, inner breaking strength. And what we have done is we have calculated a weak point. So weak point strength should be less than 3870 pounds. So uh, we can put this value here, and we will get in return, we will get the armor strength. So the total number of armor is 10.8, and putting the values, we will take it, we will round off to the near armors, because if we take it to 11, for instance, we can take it 10.8 or 8 10. We got two options. We get the 10.8, and we just put that into total number of armors, and we multiply that number. That number would come out greater. And from the previous slide, we know that this number should not be, weak point rating should not be greater than this number. If we put 10, 9, then this number will come out be greater than this, which will violate. So we will make an inner armors. You can read it. So the other concept that what we will use is so if we have we by the weak point calculation, we have calculated outer armors, and we have considered a weak point, and was and sort of tool got stuck. So what we can maximum save full way that we can apply, maximum that we can apply to our wireline without unintentionally breaking the weak point. So the formula is weight of cable in mud at that depth, so that changes with the depth, maximum save full, and 66% of the weak point rating is on that cable head. So that is not a single number, that depends upon the weight of the cable in mud at that depth. So, uh, what we can use, so for instance, our tool is stuck at 5,000 feet. So what we want to know is what is the weight of the cable uh, at that weight of the cable at that depth, so that will correspond to the tension. Okay, so if 162 multiplied by 5,000 feet plus weak point rating into 0.66, so this way we will get the maximum safe pull. Now a tool get stuck at 11,000 feet, for instance. This is the tension that will be appearing on your tension measuring device. This is not the tension at your weak point. So remember, this is very important. This is the tension that will be appearing at your tensioning measuring device. This is the tension. If you apply, if at the top, I like I explained earlier, if the tension at the top is 3160, then the tension at this point will be 3570. Okay. Now the other formula is